If we look at the valence shell configuration of carbon, we find 2 paired electrons in the 2s orbital and 2 unpaired electrons in the 2px and 2py orbitals, one in each. To fulfill the octet rule, carbon must use its. However, only unpaired electrons can bond. That means that the 2 paired electrons occupying the 2s orbital must become unpaired before they can bond. Now the 4 electrons appear to be ready for bonding, but there is a problem. The 2p orbitals are known to be at right angles to each other. If bonding occurs in the state, the 3 equivalent p electrons would form 3 equivalent bonds oriented at 90 degrees. For each pair of electrons, the s electron would form a bond of a different type and orientation from the other 3. No such compound exists. The simplest hydrocarbon, methane, CH4, is known to have tetrahedral geometry, where the 4 CH bonds are all equivalent and positioned at 109.5 degree angles to each other. In addition, there are some carbon compounds where the bond angles are 120 degree or even 180 degree. The shapes and relative positions of the valence orbitals in atomic carbon do not explain the shapes and relative positions of the bonds in carbon compounds. Hybridization theory attempts to explain the actual shapes of molecules by invoking the formation of hybrid orbitals during, or prior to, the bonding process. Going back to the carbon model with 4 unpaired electrons in the valence shell, we can take it as a point of departure for the formation of hybrid orbitals. The first step is to take either 2, 3, or all 4 of those orbitals and equalize their energies. Let's say that we take all 4 of them and form 4 equivalent new orbitals. These orbitals are now of the same energy, which is intermediate between those of the original 2s and 2p orbitals. At the same time, we cannot name the new orbitals s or p for their neither. We have to find a new The process that leads to their formation is called Sp3 hybridization. All 4 sp3 orbitals that result from this process are equivalent. That means that they have the same size, shape, and energy. According to Vesper, valence shell electron pair repulsion theory, such orbitals will orient themselves in 3D spacito be as far apart from each other as possible. The resulting shape is then a tetrahedron, where the carbon nucleus is at the center and the orbitals point to the corners of the tetrahedron. The ideal angle between orbitals is then 109.5 degrees. When an sp3 hybridized carbon bonds to hydrogen, it forms methane, whose geometry is known to be tetrahedral. A 3D representation of methane. Bonds that are positioned on the plane of the paper. The single lines represent bonds that are positioned on the plane of the paper. The broken wedge represents a bond going behind the plane of the paper towards the back. Hydrocarbons. Hydrocarbons are substances containing only carbon and hydrogen. Hydrocarbons are classified into the following major categories: alkanes, alkenes, alkynes, and aromatic hydrocarbons. In the following pages, we will overview the basic characteristics of the first 3, but will postpone the study of aromatics. Lanes and sp3 hybridization of carbon. Alkanes are hydrocarbons where all the carbon atoms are sp3, hybridized, all bonds are single bonds, and all carbons are tetrahedral. Methane is the simplest alkane, followed by ethane, propane, butane, etc. The carbon chain constitutes the basic skeleton of alkanes. Carbon chains with 4 or more atoms can be linear or branched, as can be seen from the above examples. Alkanes have the general formula CnH2n+2, where N is the total number of carbon atoms. This holds regardless of whether the alkane is linear or branched.